Okay, folks, we might get going. Again, welcome to one of our first Earth Observation Australia community webinars in a little while. And today we're extremely fortunate to have Dr. Erin Urquhart and Dr. Lachlan McKinna presenting on NASA's forthcoming PACE mission and looking at what we could potentially do in Australia with using those data, but also potentially contributing to the mission as well. Just as a reminder, in terms of logistics, we will be recording this, and so audio and video is recorded. Anything in the chat window is also recorded. If you do have questions, please keep them to the end if you want, or type them into the chat window, and we will come back to them at the end. And also, if you have comments or insights that you wish to add, please put them into the chat window as well. If you do have any technical difficulties as well, please let us know and we'll try and resolve what we can at this end. If there's any technical problems on our end, you will probably all go to a waiting room and then we'll come back on once we've resolved things as well. And just a reminder that this is an Earth Observation Australia event, and we do have a code of conduct for participation in these and our face-to-face events. Larissa's just posted the link to that on the website there, and that's really just treating everybody with appropriate respect in terms of listening and talking with one another. So before we begin, I do want to acknowledge the country on which we're meeting, and in particular acknowledge the traditional custodians of the lands and waters across Australia and other countries on which we all work and are meeting today, and pay our respects to their elders past and present. We also extend that respect to Aboriginal and Torres Strait Islanders who are joining us today in the meeting. Earth Observation Australia wants to specifically acknowledge the Quandamooka, Turrbal and Yagara peoples, who are the traditional custodians of the lands and waters where our staff live and work. And finally, and most importantly, we want to stress that Earth Observation Australia is committed to contributing to a just, equitable and reconciled Australia, where we recognise and build our shared knowledge and experiences, which is critical for a discipline area like Earth observation. I know a number of you are probably joining this for the first time today in terms of Earth Observation Australia. We're a national body, doesn't pay, so you don't have to pay to join, and we aim to represent all people who collect Earth observation data and transform it, process it and use it, so we can do all of those things more effectively, and build and maintain an effective community in terms of what we're doing. So without further ado, I'm going to hand over now to Dr. Lachlan McKinna and also Dr. Erin Urquhart to provide their parts of the presentation today. So I'll stop sharing my screen and I'll hand over to Lachlan and Erin. All right. So, all good, Lachlan.
Thank you, Stuart. Just try and get the screen shared here. Sorry, guys. Funny how this works when you.
And just while Lachlan's doing that, there are links which you'll see later on to the PACE mission, and you'll also be able to access a recording of this a little bit later on in the week if you wish to go over things as well. And I guess the other fill in, so thanks Larissa, she just posted the PACE website there as well. All right, and I'll hand over to Lachlan now. All good, Lachlan.
Okay, thanks Stuart. Hopefully I'm sharing the correct screen there now.
Yeah, you are.
Okay, great. So today, Erin and I are going to talk about the PACE mission. You might have heard about the Plankton Aerosol Cloud. Advance there. Mission and some opportunities for Australian research and applications. I'm based here on the Sunshine Coast, but I'm affiliated also with NASA Goddard in the United States, and as is Erin. I'm going to speak first, give you a bit of an overview of the mission, talk about the observatory and the sensors that will be aboard, and then Erin's going to discuss the PACE applications and early adopter program and some opportunities for community involvement. So part one, that's me getting to know the PACE mission. So it's a bit of a boot camp, I guess, of what we're about and where we're at. So I'll give you a bit of a mission history, some updates hot off the press, discuss the three instruments, the primary instrument, which is the ocean color instrument, and 2 polarimeters, which will be aboard the observatory, discuss science and data products, as well as data availability, formats, software, and where you can learn more about that. And before I continue, I just wanted to give a big shout out to the PACE project. There's a photograph there. You can see it's a large team of scientists and engineers that are pulling this all together. It's a big effort, and it's been going on for a number of years now. Okay, so PACE, the Plankton Aerosol Cloud Ocean Ecosystem Mission. We know NASA, we love our acronyms, so it's a mouthful, but PACE. So currently, let me just check here whether I'm using the, sorry guys. Okay, so currently where the mission is at is phase C, with, A, B, C to D. Phase C, essentially, we have all the elements have been built, engineering test units have been made, and we're proceeding to the testing and making the flight units integrated into the observatory. So launch was originally delayed due to COVID-19. We were scheduled a couple of years earlier, but we've had, obviously, it's hard to get in and do physical testing during that period. So currently, the launch is scheduled for January in 2024. And as I mentioned, there's a number of components now, including the ocean color instrument, that are undergoing thermal vacuum chamber testing at NASA Goddard. Outside of the actual physical spacecraft and mission itself, there is a science and applications teams, which have been competed within the United States. They are through NASA Roses Awards. So there was a first science team for PACE was assembled back in 2014. We're up to the second one now, which was formed in June 2020. They have a 3-year award, and they're working on various applications of aerosol, ocean, and cloud science to support the mission, new algorithms and such. There are also 2 system vicarious calibration teams that have been working on developing 2 systems for vicarious calibration of the ocean color instrument. There's also an applications program which was started in 2020, and Erin's going to tell you all about that, so I won't need to go on there. So the little spacecraft you see here flying towards you is what a little rendering of the of what things will look like once it's on orbit. It's about the size, the spacecraft itself is about the size probably of a minivan. You see the ocean color instrument is sitting on the back facing towards us with the big radiator, and the 2 polarimeters will sit just down on the other side. It's the next great investment for NASA in ocean color, cloud, and aerosol data records. And we need this to enable continued advanced insight into our oceanographic and atmospheric responses to climate change on the Earth. It's a mission that will do ocean biology, ecology, biogeochemistry, as well as atmospheric sciences, cloud and land. As I mentioned, there's the primary instrument is a hyperspectral radiometer, the ocean color instrument being built at NASA Goddard, and there are 2 contributed multi-angle polarimeters. The first one, HARP2, is being contributed from University of Maryland, Baltimore County, and the second one, SPEX1, is from Esron Airbus collaboration in the Netherlands. Brief history, concepts, thoughts about hyperspectral ocean color mission began almost 20 years ago. The science definition team report was handed down in 2022, outlining kind of what the proposed mission should look like. We had our first science team assembled in 2014, and then come 2015, the PACE mission was directed to NASA Goddard, and we progressed since then. The legacy instruments, obviously, that the ocean color radiometer are built on are CWIFS, MODIS, and VIIRS, and we have Polar and MISA as legacy sensors linking back to the multi-angle polarimetry. We're scheduled for launch in January 2024, which is, I think we're 16 months out, so it's coming up quick. It's going to be aboard a Falcon 9 from Cape Canaveral, which is very interesting for us, because usually these Earth observation missions tend to be launched from California, so people can probably sit on the beach and watch the rocket go up. The observatory will sit at 676.5 kilometers altitude. It'll be a polar ascending sun-synchronous orbit at 98-degree inclination and a 1 p.m. local equatorial crossing time. The mission has a 3-year design lifespan, but they'll be putting 10 years worth of propellant in the tanks should they go, obviously, beyond the prime mission phase. So just to zoom in, the hyperspectral scanning radiometer, the ocean color instrument, will be have contiguous radiometric bands from 340 nanometers through to 890. They'll have a 5 nanometer full width half max and at 2.5 nanometer steps. There'll also be 7 SWIR channels as well, which have been strategically placed for atmospheric correction over complex waters, as well as cloud and aerosol science. The ocean color radiometer is built, if you're familiar with the CWIFS design, that was a rotating telescope instrument, and the ocean color, the OCI has a similar design. So essentially you have a single science pixel that scans across as the sensor flies along. This is useful because you can mitigate some issues that you often have with, say, a push broom design, where you have striping artifacts and multi-detectors, which it can become complicated to do your calibrations and drift characterizations. The mission will have the OCI will have a 1 to 2 day global coverage, and the pixel size at nadir is 1 square kilometer. Importantly for this mission, and again analogous to CWIFS, the OCI will tilt to avoid sun glint plus or minus 20 degrees fore and aft. The sun glint, for those who are not ocean folks, it's a specular reflectance off the surface, and it can contaminate, or it does contaminate, our radiometric observations, and it's very difficult to correct out accurately. So you tend to have a lot of data loss through not being able to, being basically blinded by the specular reflectance off the surface. So the tilt is really important to help us get a lot more data from the observatory. We'll have a twice monthly lunar calibration, and there'll also be daily onboard solar calibration. So I think, I'm not sure if this is the latest slide. Essentially, where we are with updates is I believe that the OCI has been now mated to the tilt mechanism, and it's actually undergoing thermal vacuum chamber characterization and testing at the moment, and it will be there probably till October, as well as the spacecraft bus, I believe, is undergoing testing as well right now. For those of you in the community who may be data users or data providers, so you take ocean color level 1B radiometric products and it processing your own level 2 and level 3 products. For the OCI, we've assembled a number of level 1B test products, level 1 simulated data that you can take and sort of crank the handle through your processing chain if you should wish. They're available from the Ocean Color website there at NASA. Yes, so this is not my latest slide, but not to worry. I think I remember. So the UMBC instrument, the UMBC polarimeter, will be mounted here on the lower side of the spacecraft. It's the hyperangular rainbow polarimeter HARP, and it was delivered to Goddard in Q1 2022. Now it did undergo some damage during the original testing, but that's a good thing because we want things to break when they're being tested rather than when they're on orbit. So the sensor has been rebuilt, and as I believe it has been delivered to Goddard for testing, and is scheduled for integration with the observatory in the later part of this year. The ESRON Airbus spectropolarimeter for planetary exploration, the SPEX-1, the flight unit was integrated onto the spacecraft to then make it an observatory in June, and there is also simulated data available for the SPEX-1, again, for those folks who might want to think about testing their own in-house processing software. The specifications for the two polarimeters are up there on the right-hand side. The main difference between the two is HARP is a multispectral instrument, whereas SPEX-1 is a hyperspectral. There's some slight differences between angular resolution, and there's sort of that trade space between hyperspectral versus the multispectral is, data transfer and viewing geometries. So the HARP2 has quite a wide swath width, which is very similar to the OCI instrument at about 1,500 kilometers at nadir. So you'll get global coverage from HARP2 within about 2 days. Whereas for SPEX-1, it's quite a narrow swath width at nadir, about 100 kilometers across, meaning that it's about a 30-day global sort of coverage. Pixel size is very similar, and the two are based on heritage instruments, the AirHARP CubeSat and AirSpecs. So talking about data products, I'm just going to sort of work from the top of the atmosphere down to give you an idea of the kind of things, the kind of data that and information that we're wanting to get from this observatory once we're on orbit. So within the aerosol realm, we want to be looking at data products that tell us about concentrations of brown and black carbon, looking at aerosol optical properties, absorption, depth, size, distribution, and height and layers. And we're looking at cloud optical depth, height, and thickness, but also moving into some of the microphysical properties as well, such as cloud phase, liquid ice, droplet size distributions, and ice crystal shapes. And then obviously, once we get down below the atmosphere, we're measuring ocean reflectance, white cap fraction, and angular light distribution. Some of the neat things that we should be able to do when we're looking with our polarimetry, as well as the multi-angle, is such examples such as oil slick detection. Once we're down in the water column, the kinds of things we're looking at which may be of interest to the community, we'll have light penetration, looking at the angular light distributions as well as the index of refraction. The next group I would probably more familiar with, the apparent optical properties and inherent optical properties, so light transmission, absorption and scattering properties, as well as photosynthetically available radiation. One important thing about the mission is, in the past we've had multispectral ocean color instruments. One of the key data products that we've been interested in is chlorophyll, as a measure of phytoplankton biomass, but unfortunately chlorophyll in its own doesn't give you necessarily an indication of the phytoplankton types and the community structure. So with PACE, we're moving beyond bulk chlorophyll to look at the types and relative concentrations of photosynthetic pigments and fluorescence, which then can inform us of plankton communities themselves. Of being a climate mission, we're obviously interested as well in concentrations of particulate carbon and suspended matter. We also had members of the science team looking at bathymetry and classifications. Obviously, it's a 1 kilometer pixel, but there's still some interesting science you can do there. And last but not least, I mentioned aerosols, clouds, the atmosphere and the ocean, but we mustn't forget we can also do work deriving level 2 and level 3 products for land albedo and vegetation indices as well. So if you want to see the full spiel of the actual data products described, you can go to the PACE Ocean Color website, click on data, and drop down to the data products table. You will not be disappointed. I also just wanted to quickly run through the data level types that we will be distributing for the mission. The ones most folks will be interested in who are data users would be the level 2 and level 3 products. Level 2 will be swath resolution science products, whereas level 3 tend to be temporally and spatially binned and mapped data products. And these will be freely available from the Ocean Color web, also known as the Ocean Biology Distributed Active Data Center, I think OBDAC. Might have got the acronym wrong there. And you hop on the Ocean Color web, go to data, and you can search for what you will need by level 1 and 2 and level 3 browser. These are all NetCDF compliant, self-describing data formats, so they should open with most of your familiar GIS softwares. If you want to learn more information about the data levels and the data products, this is fully described on the Ocean Color website. If you hit the missions tab and find the PACE mission, this page will open up for you and you can find this documentation. Also mentioned that we have software tools available for the community to visualize and manipulate the data products that are distributed. This is CDAS, some of you folks may be familiar with. It's the front end is essentially a GIS style software, but the nice thing about CDAS is it attaches, the back end can attach to our Ocean Color processing software suite, the OCSSW, which is the exact software we would use to process from level 1B down to level 2 products. There's a lot of options in there. Say you might want to try different atmospheric correction parameterization, or there might be some non-standard products that we don't distribute. You can go ahead and process your own data from level 1B down to level 2, all the way to level 3, depending on your capabilities using this software. And again, it's freely available under the software tools. And finally, as I mentioned, there's some simulated proxy data for those of you who are data producers. You may want to test your capabilities to handle these large hyperspectral OCI data sets on your systems. You can grab those from under the data access. It'll drop down here. There's simulated proxy data and also pre-launch instrument characterization. So if you want to know the things such as the spectral response functions and those kind of things. So before I hand over to Erin, there's also a dedicated PACE mission page, pace.gsfc.nasa.gov. Under this website, we have so much information about the mission. We have a lot of updates every time news comes in. It's dropped on the website. There's instrument information, a whole bunch of information about the applications and early adopters, which Erin will speak to, links to the simulated data sets, and very importantly, the tech memos. So everything that has been done to get the mission to where it is, we document and publish through NASA tech memos. All our presentations and community outreach and education resources, you can also find those there. And the at NASA Ocean socials if you're so inclined. Some takeaways: the OCI Ocean Color instrument will be the first ever truly global hyperspectral UV to NIR instrument taking measurements of the ocean and the land and the atmosphere. Of course, and I should mention you've got 7 multispectral SWIR channels in there. The polarimeters are highly accurate, and they'll give us a view of the ocean and the atmospheres that we haven't been able to do before, and the synergies with the ocean color instrument make it a very unique mission. All the data and software will be made publicly available with documentation. Data latency is about 3 to 12 hours on average. There's, as I mentioned, the simulated data is available online for you to use, but obviously will periodically be regenerated when we learn more about how the instrument is performing on orbit. We do anticipate hosting training events in future, so watch this space. So just some final points, just PACE OCI, we're extending and improving on heritage, modus and VIIRS for ocean and aerosol data sets. And what's really interesting is these multi-angle polarimetry capabilities that will help us with especially the aerosol characterization, which hasn't been done for this kind of mission before. And with that, I will hand over to Erin. I'm not sure if this is I'm not sure if this is the latest presentation, Erin. I'll just double check, but in the meantime, I'll let you take over. I don't know if you made many changes.
I made a couple, and I just downloaded it, so I might try to share my screen real quick.
Yeah, I had a couple on the vicarious calibration. I can circle back to that if anyone has any questions.
Okay. Yeah, if you want to stop sharing, I can share real quick and we can just kick off from the updated slides. Perfect. All right, let me get there.
Cool. So just while Erin's doing that, just a reminder, if you do have questions, and I see there's a couple, just type them into the chat and we'll come back to them at the end of the presentation, so we can ask both Erin and Lachlan questions. So Erin, over to you.
Yeah, and I assume you can see my slides now?
Yes, all good, thank you.
Okay, perfect. All right. Well, thank you for Lachlan for giving the technical side of the PACE mission. I always appreciate that, as my bread and butter is kind of applications. So before I really jump into the goals of the PACE application program, I wanted to talk about the background, just so for people that aren't really familiar kind of with NASA missions. So the NASA PACE mission is one of NASA's first NASA decadal survey missions. And so what that means is that the US Congress has mandated PACE to have an applications program incorporated into our mission framework. So in addition to all the work and research being performed by PACE Project Science and the PACE development team that Lachlan just introduced, PACE Applications, which is me and my team, is focused on engaging users in the development phase of the mission to identify the utility of PACE data beyond that just of obvious research. So what Applications is really looking for is societal benefit, policy, and decision frameworks. So we have 3 main objectives of our program. The first one is to build partnerships between PACE data users and PACE data producers. We want to do this to really make sure that we're addressing community needs and concerns with PACE data before launch. Our second objective is to grow the relevance and sustainability of PACE. And then lastly, we hope to quantify and demonstrate the socioeconomic value and utility of PACE data. And the overarching goal of the PACE Applications program is to foster new partnerships and out-of-the-box thinking that will generate inventive solutions that aid society. So just before I get started, I want to make sure we're all on the same page with some applications terminology. So here at PACE, we use the word application, and that term gets, I've noticed, thrown around a lot depending on kind of an industry. For our purposes for NASA PACE, application isn't just the use of information, but it's the use of information for decision-making activities. They have to have some societal link and some societal benefit. So applications are the link or bridge, if you will, connecting PACE to society. Applied research provides fundamental knowledge of how a missions data product can be scaled and integrated into a user's policy, business, and management activities to improve a decision-making process. When we talk about users, we're really referring to a broad community of individuals or organizations. This can be the private sector, the public sector, who will be applying satellite data at all different scales of decision making. And lastly, stakeholders are those who are affected or affect an action or a policy. So these are often the decision makers who contribute to policy development. And in our terms, stakeholders are the users of applications and often are the ultimate group that the applied sciences serves. So as you saw with all the data products that Lachlan showed, the PACE mission and the applications program really supports a very wide range of interdisciplinary applied sciences. What we really focus on is looking at air quality and public health, water resources and water quality, climate, ecological forecasting, and disasters. And we also have included, to a smaller scale, supporting kind of terrestrial and land applications as well. So unlike a lot of other NASA missions that focus on one or two, ecosystems, PACE will benefit varying levels in different Earth systems and different application areas. So I have a couple different things popped up here in terms of kind of societal applications that PACE will support. So here at PACE, I firmly believe that before we can quantify and demonstrate the value and the impact of PACE, that we really need to understand the PACE community. The data priorities, the goals, the needs, and importantly, the barriers and gaps with using remotely sensed data. So rather than prescribing a value and, we as scientists assuming that we know what the community needs, we've really made it a priority to involve, engage, and co-produce research and applications with our community. This is helping us really understand what the community needs and how PACE data products can, benefit them before launch. So in doing this, we have started asking questions about data usability, accessibility, and remembering that those two terms don't mean the same thing for any two users. With the PACE user community, we have defined what usefulness means to different types of users. We've gathered feedback on priorities and what would make PACE data and the data experience useful to them. And more recently, we have started collaborating with the community by collecting specific examples of how user communities think that different data barriers can be addressed. And this is ultimately to help ensure that PACE data is accessible, usable, and actionable at the time of launch. So these next couple slides, I'm just going to show you something that we refer to as user personas. They're kind of well used within a lot of different industries. But these are 8 different hypothetical PACE users within the water community. And what we're using these for is, rather than a bunch of scientists and developers getting together and say, PACE data needs to look like this, this, and this, and it needs to have this different data discovery and these different tools. We've kind of started to kind of understand our community so that we can better kind of personify those needs. And so these are 8 different personas that we developed in a focus session that we hosted last year with our community. And with the community, we went around and we identified as these different users. We kind of got in the heads of these fake people to understand what they need, what are their goals, what does that ideal data experience look like for these individual people. Again, these aren't just application users, we want to be inclusive. And so we think about everything from academic postdocs to people that work in regulatory agencies to international agencies. But again, it's really about understanding the PACE user community and not just understanding them from the sidelines, but really understanding them through the co-development and collaboration with the community. And so after we went through all these different exercises with our user communities for these personas, this is kind of what the persona looks like. So just kind of, so you can get an idea of how we think about communities. This is a stereotypical, water quality manager in the state of Florida, the United States, who works on harmful algal blooms. And so with the community, we all brainstormed and we came up with kind of this type of person like Tom. What are his goals in his day-to-day job? What are the frustrations that existing data sources and data tools are proving? And, thinking about what does the perfect experience look like? What kind of data does this person need? Has really helped us at PACE be able to kind of pinpoint how the PACE program can support someone like Tom. So we've done this across both the water quality sector as well as the air quality and human health sector. All right, so on a previous slide, a few slides ago, I mentioned that the main goal, or one of the main goals of the PACE applications program, is to foster new partnerships. So this is where something called the PACE Early Adopter Program comes in. The aim of the Early Adopters Program is to engage users and build broad support for PACE applications through transparent and inclusive processes before launch. So the program aims to promote applied science and research designed to scale and integrate into activities that benefit society and inform decision-making. So I've listed a few different goals, and these are goals that are both beneficial to the early adopters as well as beneficial to the PACE program and NASA as a whole. NASA has about 11 different missions that have early adopter programs, and we kind of all have the same big goal, is to support users before launch so that we can accelerate the uptake of data once we're on launch. So we want to figure out kind of all the issues and the kinks of the data with our communities who have kind of pre-existing applications so that when we're on launch, we're ready to go. So the program launched in February 2020. We currently have 26 early adopters that span, in the green is everyone that's working in water quality and water resources. We have in the yellow or the orangish color is kind of people that work in climate, disaster, and terrestrial applications. And then the blue here is folks that are working in air quality, public health, and disasters. So these early adopters are individuals or groups, like I mentioned, that have very clear and defined use of how PACE data can be used to benefit society. They're groups that, they have pretty good expertise with remote sensing data, be that multispectral data, but they can actually work with some of that pre-launch data that Lachlan mentioned. For developers, that might be like a level 1B simulated data file. For a lot of these folks, we're looking more at kind of level 2 and level 3 types of data products coming from PACE, which the simulated data is coming down the pipeline for that before launch. And so like I said earlier, the intention of the early adopter program is to really help these folks and its ever growing kind of application to get their hands wet and to really understand the ins and outs of PACE data in their existing applications so that, again, by the time we're on orbit, these folks are ready to plug and play in their models or their applications or their data tools. So I wanted to go through two different examples of a couple of our early adopters. One kind of working in air quality and public health, and the other in water. So the first is Dr. Heather Holmes. And Heather plans to use PACE hyperspectral and polarimetric data to track smoke plumes, to improve emission modeling, and to determine air pollution sources in the United States. So why is this important? So the Western United States is home to 70+ million people, where many of those counties violate at least one criteria of the pollutants according to the United States Environmental Protection Agency. So Heather's work will improve the air quality and exposure models of elevated PM 2.5 concentrations. Oops, pardon me. Let's get back. There we go. Concentrations due to temperature inversions and wildfire smoke in the Western United States. So furthermore, her work is going to assist in epidemiologic studies, and she hopes to provide more accurate, refined smoke forecasts to aid in air quality alerts and human health advisories. So how Heather plans on using PACE data is the continuity of aerosol retrievals that she's currently using in MODIS, MIAC, and MISER. With the hyperspectral aerosol retrievals and the multipolarimetric data, PACE is going to help reduce the uncertainty of smoke plume injection height in aerosol retrievals. And in terms of who Heather is working with, she's working with local air quality districts, regional public health departments, as well as, she's an academic professor, so she's working with early career researchers, her own PhD students and postdocs. So the second early adopter that I wanted to highlight is Dr. Richard Stump and his co-PI, Shelley Tomlinson, and that's at NOAA in the United States. So Rick plans to use PACE hyperspectral remote sensing data to separate out different types of harmful algal bloom types, both in inland lakes, coastal beaches, and estuarine environments. So probably not a surprise to a lot of people, but certain algal bloom species, specifically for Rick's work, cyanobacteria species, produce toxins that produce a significant threat to human health through recreational drinking water exposure. So PACE, through Rick's work is going to support targeted harmful algal bloom management, to advise state managers, local health departments, water treatment plants, aquaculture, commercial fish and industries. So ultimately, using PACE data to advance and retune these algorithms with hyperspectral data is going to better protect public health and from toxic algal blooms. And so with the PACE hyperspectral ocean color instrument data, it's going to assist their work in separating bloom type and estimating the physiological states of blooms. And who Rick and Shelley are working with in terms of their stakeholders is they work with state managers in nearly every state in the United States that has lakes. But specifically for this project, they're working with the states of Florida, Maryland, Virginia, Ohio, and California. All right, so kind of talking about the early adopter program a little bit more as I'm watching the clock. So the benefits of working as an early adopter, you've heard me talk about partnerships a few times. It's really networking and partnership opportunities. As an early adopter, you get to participate in all of the PACE application and PACE mission activities. You have collaboration opportunities with other PACE early adopters. The big two here on the bottom are listed is partnerships with the Ocean Biology DAC and a science team member. So as part of the PACE mission, we have a funded 3-year science team of 20 different members. And so every single early adopter is formally partnered up with a PACE science team member. So we have users that are not associated with NASA are partnered up with funded science team members to build collaboration and address any issues. And then lastly, the simulated data and the proxy data that Lachlan mentioned, early adopters kind of have first light access and they learn about these simulated and proxy data sets. Oops. So in terms of eligibility, real quick, so in order to become an early adopter, the big thing that separates this program from a lot of other programs is that these folks that want to apply, they need to be working with an existing application or have an innovative idea how PACE data can directly support decision-making activities. So direct impacts to society. Applications, like I showed with the previous 2 examples, they should be working in close coordination with their users or on behalf of their stakeholders. These folks are, interested in learning about PACE data, obviously, but looking more into the research and the developmental products. And then lastly, it's really, as we're trying to kind of quantify the impact of PACE data, the willingness to provide testimonials on how PACE data is going to improve decision-making over heritage multispectral. So if you're excited, if you want to be an early adopter, I put the QR code there that you can scan to kind of learn more about the program. And lastly, I know it's been a little bit of a shameless plug on my part, but one more big announcement coming up is next week, actually, we're hosting our annual PACE applications workshop. So this is our 3rd in a series of 3. And so this is a big 2-day virtual workshop where we're inviting everyone from, our flight project representatives to project scientists. Lachlan's going to be there speaking with a kind of a slew of other PACE project scientists. And then the second day, we really get into topics about community involvement and engagement and why that's important. We're going to start talking about data discovery, data accessibility and usability and what that means to different types of communities. And then lastly, we're going to explore kind of an example of oil spills mitigation and response and how working across 4 different NASA missions can really fill the gaps and make all those individual mission data products much more strong by working together. And if you're interested, there's also another QR code there that you can register for the event. And I believe that's it for me.
Awesome. Thanks, Erin. There's so much in there from both what you and Lachlan have presented that's relevant to, I think, one, for our communities to engage with what's happening in this mission. And I think two, given the state at which I guess Australia's communities are in trying to develop missions, including one which is around coastal and inland water quality, that engagement program is really eye-opening. So thanks very much for doing that. So also I did want to acknowledge both Erin and Lachlan for their time today, particularly Erin. I know it's late in terms of where you are time-wise, so thanks for doing that. So we'll move on to questions now. There are some questions in the chat window, which I'm going to go to. I did want to point out, again, Lachlan's put up the link in the chat window to the PACE page, the workshop, which Erin's just mentioned, which I think, Erin, that had a virtual component to it, didn't it?
Yeah, it's completely virtual.
Oh,
yeah.
completely. There's the link there, and I'd really encourage people to look into that, particularly from an atmospheric component where it's aerosol, dust, or whatever. It's really good to see multi-angular measurements sort of back on the agenda again, but also for the oceanic and coastal things as well. I'm just going to go to the first question, open to either of you to answer. It's from Tim Malthus at CSIRO. And the question was, does the single science pixel mode of acquisition influence the signal to noise ratio? And I think what Tim's inferring is that you've only got a short amount of time, a dwell time over each pixel to measure photons. So is that good or bad?
So yeah, this is something where the engineers pushed the envelope. Like it's something that we wouldn't ordinarily think about, but the actual the optics and the way the focal planes are set up is particularly like groundbreaking stuff. But it's sort of tend to sit in the background and think about it as engineering. I've just gone back to remind myself, and I'm no expert on this myself, but I believe that the slit width is 16 kilometers or 16 pixels across, and they have what's called time delay integration. So as you do a scan, you've got 16 pixels, but you kind of build up one science pixel. It kind of adds it all together as it goes along. So that's not a great explanation, but yeah, this was and I remember when this was all being put through the design process. This was a big challenge, but we have got reached the requirements for the signal to noise, which I believe is, I think we're over 1,000 in the blue and doing well in the red. The blue and the red focal planes are actually separated, and there's a dichromatic. Essentially your light comes in through your telescope, gets split into the blue and the red focal planes, then onto the SWIR channels, which are at the end. But I'll put a link to a paper here by the instrument engineer, and yeah, Tim, that's the best I can do. I'm sorry, but yeah, that's a really good question, and that's actually something that sits in the background, but it's really cutting edge kind of stuff.
Thanks, Lachlan. So yeah, if you could put that link in, and again, I'd refer people to the PACE website, because there are some of the instrument specifications up there, and I think that is a really critical point. That's been a limitation for spaceborne hyperspectral, is having enough signal in there, particularly over water bodies. Just before we go to the next question, Erin, that model of community engagement you talked about seems a little bit different to what we've seen before from science missions. Is that something that was developed uniquely in PACE, and is it going to be used in other decadal missions as well?
That's a really good question. It is a little bit of an experiment with PACE, and that's just because of my own passion, to be completely honest with you. Up until 3 years ago, I was a research scientist and kind of saw how I was engaged with incorrectly. And so I've really kind of pushed the PACE applications program and the PACE mission to really make community involvement and co-production and co-development, kind of the words that were in that model, kind of the forefront of our program. There has been a lot of interest in what we're doing from other decadal missions, to be honest. And so we're working on some manuscripts to try to get this proof of concept and examples, because people are, like yourself, people are starting to realize that we're doing it a little bit differently, and that it's a little bit more effective and sustainable with our user community. So I, offline, or if anybody's interested, I would be happy to kind of talk about how I've developed the model and kind of the programming. But yeah, absolutely.
Right. Thanks. I think we will definitely be in touch with you.
Absolutely.
I guess the last follow-up on that is, do you think it makes a a difference? I mean, you mentioned sustained engagement with the users and the stakeholders, but in terms of the people who are approving the next steps in the mission, do you think it carries more weight with them?
On the NASA Applied Sciences side, absolutely.
Okay.
You know, and from what I can say is for the PACE mission, the application program kind of came in, it was a little late in the game, if I will. So a lot of the decadal missions that after PACE, they're bringing in the community engagement and the community assessment and stakeholder engagement pretty much at the same time that they're formulating missions. So I am aware of the fact that a lot of the kind of the groundwork that we've set with PACE applications is being it is influencing kind of future missions, which is great, and you know, a huge compliment to the PACE mission. And so yeah, I guess it's kind of hard for me to answer that kind of at the, you know, the powers to be, but I do know that kind of at the headquarters level of NASA, they are looking at what PACE is doing.
Cool. All right, thanks.
I hope so.
Yeah. All right, we'll be in touch on that. Just going to the next question from Robbie Bishop-Taylor, Geoscience Australia. It's in relation to metadata. So I think, Lachlan, you'd shown that all the products are in sort of net CDF, I guess, but Robbie's question is like, are there plans for providing, you know, a spatial temporal asset catalog sort of form of metadata to make the access easier?
That's a question I'll have to get back to you, Robbie. That's probably a question for Sean Bailey, who's the director of the Ocean Biology Distributed Active Archives Centre. So the mission has certain components, and the OBDAC is responsible for the data processing for the whole kit and caboodle and the distribution, including, you know, not just ocean, but also the atmospheric products. But that's yeah, sorry, I don't have an answer for you today, but
That's okay.
I can track one down for you.
We'll add that.
I believe, I guess all I can say is they'll be following kind of the best practice, the practices that the NASA DACs would use currently. Yeah, I'm not sure if they have a STAC at present.
Cool, thanks. All right. All right, any other questions just from the floor in the chat window, or did people want to bring up any other points? I think while people are going through that, I do want to mention Australia's proposed Aquawatch mission, which has some, I guess, a lot to learn from what PACE has been through already. So hopefully, you know, we can use this event as a way to start to build some of those links there, as we're very much at the start of the journey, pre sort of phase A, to figure out how to do things, and particularly engaging with communities as well. So this has been very insightful.
One thing I forgot to mention about the data products, Stuart, is that we've been working really hard to ensure that our distributed standard level 2 products all have associated measurement uncertainty. So we've been doing a lot of behind the scenes. I know in the community, the ocean community, it's starting to become more of an interest topic, but basically we're trying to, you know, go from our instrument model, looking at noise as well as uncertainties from ancillary data sets, and propagating that right through the software framework to give ourselves standard uncertainties, but also documenting that whole procedure so that if you get a chlorophyll product, you'll have a chlorophyll standard uncertainty as well. So that's a big part of this mission, is to make sure the end users not only have a data product, but they have something that they can then have an idea of how they feel about the quality of the data, or the especially for end users. I think that will possibly, you know, be quite important.
Cool. Right, thanks. Right, I just realised I've missed Matt Garthwaite from CSIRO's question about what are the vicarious calibration.
Yeah, sorry, I've got a slide. I've got a slide here if it's
right,
okay.
I'll stop sharing and I'll let you share that, Lachlan.
Share that one.
So I think just while you're doing that, you know, this is something that, again, we're looking at developing in Australia to engage more and give back to the international community, is having ground-based measurements as well. So.
I think that's the one. So sorry, I was trying to be prepared, and I put an old slide on my desktop, and the one in the cloud had not updated yet. So yeah, currently there's two that NASA has funded, 2 system vicarious calibration projects. So essentially, you have a radiometer, radiometric measurements in the ocean that are very accurate, and we propagate, run our through the models to do some calibration to make sure our water leaving radiances are accurate. We have there's a HyperNav concept by Oregon State University and Seabird Scientific, and this is a radiometric float that sits on the surface and can profile up and down as well. They hold at a depth so you avoid fouling and that kind of stuff. So they're quite small and portable. You can put them out for a long duration. And they've been doing some test deployments. The second concept is Marinet, which is by University of Miami and NIST, and it's a radiometric buoy. It's much larger. It's, for scale, it would sit inside like a 20-foot container. It has a 3 arms at fixed depth to measure water leaving radiance or upwelling radiance profiles to approximate your water leaving radiance. And it's built on sort of the Moby legacy. And I believe that this is a slide from Jeremy Waddell, who's the project scientist. So I believe that they're currently working to do a deployment and migration of this instrument off the coast of Perth sometime this year. Yeah, then the other thing actually, which while we're talking about involvement and validation, calibration, once we've post-launch, there is going to be within the United States, a competed PACE validation science team. So kind of the composition, scope, and execution of how that will work is still in preparation, and the selection is expected in late 2023. But we want them in the field after first light boreal spring, not austral spring, 2024. And there's also going to be a PACE post-launch airborne experiment called PACE PAX, which will be the PVST, I guess, will be trying to encompass all science. The baseline science project, science data products. The PACE PAX will be an airborne campaign out of the West Coast. And obviously you want synergies with the PACE validation science team, but this will be looking at sort of some of these hard to measure cloud and aerosol properties. So I know we're coming up to the end there, so I'll stop there. So.
Excellent. Lots going on there for us to engage with. Just one more question. So Robin Schofield from University of Melbourne. Robin, can you just briefly expand on that? And if it's a long response, we might have to take it offline.
Yeah, no, if I can just jump in. So averaging kernels are just provide the sensitivity of how the instrument measures, for example, the atmosphere largely, if you're getting profile information for the aerosols and clouds. And just wondering, it's very useful if you get that information alongside with the product. So it's a little bit more than just uncertainty provided.
All right, thanks. I don't know if Erin or Lachlan, you want to tackle that or come back to it later?
Sorry, were you talking about is it sort of profiling LiDAR or for the atmosphere? I'm an ocean person, so not an atmospheric person. We have a number of different science leads tackling different avenues, but I'll try my best.
It's really just about remote sensing when you sample something, anything really. You don't often sample the whole exactly what you want to retrieve, and that process requires some sort of integral of some form, and the integral is provided by what's called averaging kernels or smoothing kernels, like a smoothing matrix. I'm not sure what the ocean term might be, but from the atmospheric point of view, these are smoothing functions, I guess.
Can I jump in really quickly because we're at time? Robin, I'll send you a link to one of the documents within the census technical specifications, because I think we've got some slight differences of terminology here, and in terms of looking at, I guess, how the optics and point spread functions work with this
Perfect.
instrument. So that might be the easiest way to deal with this now. So cool. All right. So I'd just like to close things off formally again, and really would like to thank Lachlan and Erin for their time in preparing for this and presenting it. There will be a webinar which we'll put up, a recording of this next week, which people can access, and hopefully this is the start of some longer term collaborations between the PACE mission and a number of the missions and programs in Australia. So again, thanks everybody for attending today, and thanks to Larissa Marfan and the ELA office for setting things up. So thanks again, everyone. See you later.
Thanks,
Thank
Stuart.
you.